Okay, we start now. So is it really convenient that you sit that far? If it's okay with you, then no problem. Okay. So I'm not going to say anything much different from what is written in Milner's book, but I'm going to give, well, extended commentary if you wish. Alternatively, if you have specific questions about what you've read, we can discuss this. So anyway, please think of questions, and I will try to remind what happens. So the first chapter of Milner is basically the repetition of what you already know or supposed to know from the complex analysis course. Well, one important notion, which may or may not appear in that course, is the notion of a Riemann surface. Which is the same as one-dimensional, where this one-dimensional reference to complex dimensional over complex numbers, complex analytic manifold. And if I can assume the notion of just a smooth manifold known, then I can say that Riemann surface is, in the real sense, two-dimensional manifold equipped with some additional structure. And this structure is, firstly, the structure of complex numbers on the plane where the coordinate charts live. So we have a real 2D manifold X with coordinate charts, say phi alpha from U alpha to C, where I really identify the plane of real numbers with the plane of complex numbers. And additionally, so just for 2D real manifold, we require that the transition maps are smooth, right? We require that the transition maps be smooth. That means that if we have some, so U alphas form some open cover of X. X can be written as a union of those U alphas. And if we happen to have some intersection, say if U alpha happens to intersect some U beta, then on the intersection we have two different coordinate charts. One is phi alpha, another is phi beta, and I can draw it like that. So the intersection goes to some set phi alpha of U alpha cap U beta here, and to some phi beta of U alpha intersect U beta here. And there is a transition map phi alpha beta. So in the real case, we just say that this transition map is smooth. In the Riemann surface case, we say that phi alpha beta, which is from phi alpha of U alpha intersected with U beta to phi beta of U alpha intersected U beta, is holomorphic. Which is really a very strong requirement. because it follows immediately that you can speak of angles between intersecting curves on any Riemann surface, because you can measure an angle in any chart, and a transition map is a conformal map, which therefore preserves this notion. So it's automatically biholomorphic, because we know that this is a homeomorphism, and you know by complex analysis that a holomorphic homeomorphism is necessarily biholomorphic. Okay. Is everything okay? Now, an important theorem, which was not a part of the complex analysis course, and it's not proof in Milnor, because this is a separate story. This is a very deep theorem. But the simplest case of this theorem is just the Riemann mapping theorem. So a more general version of the Riemann mapping theorem is called the uniformization theorem. The uniformization theorem. It can be stated in different ways. One can say that any Riemann surface is covered by one of the three very specific Riemann surfaces. Alternatively, you can just say what simply connected Riemann surfaces are, because you know, again, from topology, that any Riemann surface is covered by some, it has a universal covering. Is that okay? Any Riemann surface has a universal covering, and this universal covering automatically gets the structure of a Riemann surface, because the structure of the Riemann surface can be lifted from the Riemann surface to its covering space. So the universal covering space of any Riemann surface is also a Riemann surface, and it's enough just to classify all simply connected Riemann surfaces, and the answer is as follows: if X is a simply connected Riemann surface, then either X is isomorphic, meaning an isomorphism in the category of Riemann surfaces that is a biholomorphic map, that is a homeomorphism that is holomorphic in any coordinate chart. So either X is isomorphic to CP1, which is the Riemann sphere, and this is the only compact case, or to C, or to the disk. And these three spaces are not isomorphic. Is the statement clear? So note in particular that the Riemann mapping theorem is a special case of this uniformization theorem, because in the context of the Riemann mapping theorem, what you take is you take a simply connected domain in the plane. By the way, this will be our main example of a Riemann surface. I mean, there may be different Riemann surfaces, and in principle, a Riemann surface may have complicated topology, but it's really the main example for us. What would be the main example for us is a very simple Riemann surface, which is an open subset of C. Any open subset of C is automatically a Riemann surface. The inclusion map gives you the structure of the Riemann surface. And if it's already simply connected, then the uniformization theorem tells you that it's either, well, it's one of the three cases. Now, if you know that an open set is not only simply connected, but it's also not the entire sphere, then it's not compact, therefore it's not isomorphic to the sphere. And if the complement contains more than one point, then you also know that this cannot be C. If you had an isomorphism between C and something else, then you would have a holomorphic function on C that misses more than one value, and that's also impossible. So the only case is the disk. And in principle, you can prove the uniformization theorem as much the same way as you. So the argument, the idea is basically the same as in the proof of the Riemann mapping theorem. If you recall, you considered all holomorphic embeddings, and then you pose a certain optimization problem and prove that there is a solution to this optimization problem, which actually gives you the required map, the desired map. And in the same way, you can use, you can consider all partial covariance, the covariance of, well, if X is already simply connected, you can consider inclusions of your Riemann surface to say here, and then also pose a similar optimization problem. But there are many details that really make this story more complicated than just the Riemann mapping theorem. Okay, so this will be one of the tools. Also, let me recall some of complex analysis theorems. Maybe that's not necessary, but let me state a theorem, maybe in a slightly different form, in the same form as it's stated in Milnor, but it may be slightly different from what is usually taught in complex analysis classes. So the theorem is this: if you have holomorphic, so if F from U to C, so U is an open subset of C. F is holomorphic. And takes, let me, maybe I will not do a general U. I will just confine myself with the disk of certain radius. So let me introduce notation. D of a certain radius R will stand for the open disk. So it's the set of all complex numbers such that the modulus of Z is less than R. And let me say, let me talk about a holomorphic map from a disk of radius R. Such that and such that F of D of R is contained in some disk of radius S then you have an upper bound for the derivative. So here I took the disk centered at the origin. This is, of course, you can do it in general. You can take any disk of radius R, but let me assume from the start that it's centered at the origin. Then I have an upper bound for the derivative of F at 0, and this upper bound will be just S over R. Is it okay? This is how it's stated in Milner's book. And the proof yes, this is similar to Schwartz lemma. The only difference is that actually there are two parts of the Schwartz lemma, and this is only the first part, or a similar argument or a similar statement to the first part, because in the first part you assume that the center of the disk goes to the center, and here it's slightly different. You don't assume here that the center goes to the yes, for the first part of the Schwartz lemma, you consider a map from. I will state it, by the way, but let me first be done with that. Okay, so the proof uses the Cauchy formula for the derivative. So what would be? Do you remember the Cauchy formula for the derivative? Mm-hmm. Integral. F от z. Если делить просто на z, это будет f от нуля, да? А для производной на что надо делить? На z в квадрате, правильно? Окей. So, and the only thing is that the integration is over what? Is over a circle of some, let me put it here, that the integration is over a circle of some radius r1, where r1 is only slightly smaller than r, because I want a circle that lies entirely in our disk, right? And the circle of radius r doesn't. So I took a slightly smaller radius, and then I want to estimate the right-hand side of this Cauchy formula. So the modulus of f prime of 0 is then less than or equal to 1 over 2 pi. Now, the absolute value of the integral is bounded above by the integral of the absolute value. Okay, so I can put the absolute value here, and I can say that it's some, so let me put r1 squared here, and f of z modulus dz in the numerator. Okay. So now I may have some problems with the fact that the disk of radius s in the image may not be centered at 0. Let me draw a picture here, so just in case. So the picture is this. You have a disk of radius r, and you have a map of this disk to, so here is 0, to some disk of radius s. Okay, that may be better. So let me put f of z minus f of 0 here. The derivative is the same, as you're completely right. And then I'll also put f of z minus f of 0 here, and the modulus of dz. And now this is bounded above by what? So this difference is less than or equal to s. So I write 1 over 2 pi. And I write s here. The integral of dz is just the length of the circle of radius r1. So it's 2 pi times r1. And you divide by r1 squared. So this will be, the upper bound will be s divided by r1. But r1 is any number less than r. So in particular, since this is true for any number less than r, you can also take the infimum of all this. And you'll have r in the denominator. OK. So now what happens next is that Milnor shows us some nice way of deducing various complex analysis results from this one. But maybe before doing this, let me also state the Schwarz lemma. It will be important. OK. If I put it right, Schwarz. I'm not sure about T. Is there T here? I think not. Lemma. Well, I will insert T if needed. But anyway, the Schwarz lemma says that if you have a holomorphic map without. So am I right? OK. It says that if we have a holomorphic map from the unit disk d of 1 to itself, holomorphic, then holomorphic end such that 0 goes to 0. This is an assumption now. So we assume that 0 goes to 0. Then the first part says that the modulus of f prime of 0 is less than or equal to 1. And now the first part follows immediately from what we have just proved. But the second part is also very important. The second part says that if the equality is attained here, so you have an inequality. If the equality is attained, if the modulus of f prime of 0 happens to be exactly 1, then we can say much more, namely, then f of z is just lambda z for some lambda of absolute value 1, for some lambda in the unit circle, for some lambda such that modulus of lambda is equal to 1. So it's just rotation. Okay? It's multiplying by a complex number of modulus 1 is simply rotation. And if we just know that the derivative at one point has modulus 1, this is a very strong statement. We just know the derivative at one point, and we already conclude that the map is a rotation. How we prove that? So I only need to prove the second part. And yes, this is one way of doing this. So okay, let's do it this way. So consider a new function g of z, which is equal to f of z divided by z. Now it has the limit. So the limit at z goes to 0 of g of z is equal to f prime of 0, just by definition of the derivative, and it exists. So we can also define the function at 0, and it will be holomorphic there because here is the derivative. G will just be a continuous function at 0, but by the removable singularity theorem, it will also be holomorphic. Okay, so by the removable singularity theorem, I'm not sure. Maybe Milner somehow manages to do without the removable singularity theorem, but let's do it like that. By the removable singularity theorem, G from the disk to C is holomorphic. Now we also need to use the maximum principle. So by the maximum principle, let's see what the absolute value of G can be. Now, on the boundary of the disk, the absolute value, it may not be defined exactly on the boundary, but near the boundary, it goes to 1, right? Because no, not to 1, but at least it cannot be bigger than 1, because the denominator goes to 1, and the numerator is less than 1. Okay? So on the boundary, it cannot grow larger than 1, and it's exactly 1 inside. Right? So it attains its maximum inside, which means that it's 1 everywhere. Right? So G is equal to 1 everywhere, because it's 1 at one point, and at that point, it's absolute maximum. So it's 1 everywhere, and then of course, G must be constant. Well, for example, by the invariance of domain or whatever. So a holomorphic function cannot take values only on the unit circle, because any holomorphic function takes values in an open subset. Well, alternatively, you can take what? Locally, you can take the logarithm, and then it will take only real values, and it's impossible for holomorphic function to take real values only. По теореме об устранимой особенности. Это что если у вас есть функция, которая по непрерывности, голоморфная функция по непрерывности продолжается какую-то точку, но в этой точке автоматически голоморфна. So the theorem says that if you can continue the function, if a function admits a continuous extension to a point, or just is bounded in the neighborhood of the point, it would be enough. If it's just bounded in the neighborhood of the point, then it extends there holomorphically. So that this is no singularity. Okay, and if it's constant, we know, let's denote this constant by lambda, and we know and we prove the desired. Okay. So this second part is also important. Now, what we can do with this theorem, for example, let me state several corollaries, which we know from complex analysis anyway, but as a corollary from the theorem, we can say that, well, as a corollary, I can state the theorem of Liouville, which says that a bounded holomorphic function on C is necessarily constant. A bounded holomorphic function on C is a constant. Well, f can be restricted as a function from some disk of very large radius to a disk of a fixed radius. So being bounded means just that all values of our function lie in the same disk. And the radius of this disk is just fixed. Those depend on r. However, we know that the derivative of f, say, at 0 is bounded above by the ratio of r naught divided by r. And here r naught, the numerator is fixed, whereas the denominator can go to infinity. And so this goes to 0, which means that the derivative at 0 is 0. And the same can be said about the derivative at any point, because 0 is the origin which can be chosen arbitrarily. And therefore, the derivative vanishes identically, so that the function is constant. So it's a very simple consequence. Another consequence is that there is no isomorphism between C and the disk. So the plane is not conformally isomorphic to the disk, simply because a conformal isomorphism would be a bounded holomorphic function, and the bounded holomorphic function must be constant. Therefore, it's not an isomorphism. So we already know that the three Riemann surfaces which we encountered in the uniformization theorem are really different. I mean, they are different as Riemann surfaces because, well, CP1 is special. This is the only compact. Riemann surface in the list. So it's certainly not isomorphic to the other two. Now, these two are not isomorphic to each other because we just proved that. Also, as a consequence of the same theorem, we can prove the classical Weierstrass convergence theorem. Well, I hope that I get this right. Weierstrass convergence theorem. And it says that given an open subset, open U in C, and the sequence of holomorphic functions Fn from U to C holomorphic that converge uniformly to some f from U to C. We can also say that the sequence of their derivatives is it Weierstrass convergence theorem? Maybe I'm not sure I called it right. I'm not sure that this specific statement is what one must call the Weierstrass convergence theorem. Maybe something different is called that, but never mind. So then what we can claim is that the sequence of derivatives converges to the derivative, well, maybe let me put it different. So the assumption is that this is a uniform convergence to some function. And a priori, we don't know anything about this function, about the limit function. So then what we can claim is that firstly, this limit function is holomorphic. And secondly, that the sequence of derivatives converges to the derivative of f uniformly on all compact subsets. So uniformly on compactor in U. That means if you fix any compact subset, then the sequence of derivatives converges uniformly on that compact subset. Ну, это может быть, но от того, что... Ну, можно из этого более... Нет, что можно из этого более слабого вывести более сильное, которое вы говорите. Я думаю, что... well, a version of this statement is that the assumption is also somewhat weaker. Namely, instead of assuming the uniform convergence on all of U, you can assume a uniform convergence only on compactor in U. But that may be, well, let me stick with this version. I believe in Milnor, this version is given. Proof. So first of all, f is continuous because it's a uniform limit of continuous functions. Okay? It's automatically continuous. Then we want to have some estimates on the derivatives. So this will be the first step. Then the second step is the following. So let's take a compact subset. Take a compactum K in U, and then there is some positive epsilon, so that the epsilon neighborhood of K also belongs to U. So there is an epsilon bigger than 0, such that the epsilon neighborhood of K is also subset of U. And we want to use the theorem, and we want to say that for every point Z in our compactum, F sends the epsilon neighborhood of Z to some fixed well, to some disk. Let me write it like d of R naught. And we can always arrange that, because well, maybe I should assume more than what is written here. Let me also assume that the epsilon neighborhood is compactly contained in U. Then the image of this epsilon neighborhood certainly lies in some bounded part of the plane, and the bounded part of the plane is contained in some disk of definite radius. So that the upper bound on the derivative would be f prime of z, the modulus of f prime of z is less than or equal to r naught divided by epsilon, and it's just a definite bound. Well, Fn. What's important here is that this upper bound does depend on n, and it does depend on z. It depends on the compactum, possibly. It may depend on the compactum, but otherwise it's just a constant. So the sequence of derivatives is bounded. Now, this was the second step, and now knowing that the sequence of derivatives is bounded, what shall we say? We shall say that formula? Cauchy? No, вообще общая идея, general idea is that it's much easier to deal with when you speak of uniform convergence. It's much easier to deal with integrals rather than with the derivatives, because you know that the uniform convergence of functions implies the uniform convergence of integrals if you're integrating over some bounded things. Well, you suggest to use Cauchy, the Cauchy formula here. Maybe. So the Cauchy formula for what? For the derivative, right? I'm not sure I want. Somehow we already used the Cauchy formula there, and I already wrote the consequence of this Cauchy formula. So maybe I just want to say that let's take any. So the epsilon neighborhood of k. Let me first draw. So let me first draw some picture. So here we have our compactum k, and we have an epsilon neighborhood of it. So u epsilon of k. It may look that it's connected. It doesn't have to be connected. But anyway, it has some finitely many connected components. I just wanted to. I do want to integrate something because this is really the right idea. But I want to represent the values of f as path integrals between certain limits. So f of, I want to say that, say f of z is equal to the, or fn of z is equal to the integral over some path from z naught to z of the derivative, and then do something like that. Of well, whatever the integration variable. ну, в принципе, здесь можно выделить, это как-то немножко коряво, здесь можно выделить сходящуюся последовательность, вот, и дальше все хорошо будет, потому что, ну, как-то мне не хочется, ну, и там сказать, что для любой сходящей, но, может быть, так надо сделать. Может, надо сказать, что для любой сходящейся, maybe I should say that, well, it's a bounded sequence of holomorphic functions. We can choose some convergent subsequence, and for any convergent subsequence, prove that everything is fine. Maybe I should do like that. So let's choose a convergent. Choose a convergent well, on this epsilon neighborhood or on the closure of its subsequence. I don't know. Maybe it's just easier to use the Cauchy formula. So that would be a standard proof. Milnor somehow uses that theorem, but in principle, of course, we can write that f prime of z is the integral over something of some contour around z that lies entirely in U. Well, whatever, a contour C, 1 over 2 pi I. Of what? Of f of fn. Fn prime of z is the integral of fn of z dz divided by, so here let me put z naught divided by z minus z naught squared. And from the uniform convergence of this, we get the convergence of the derivatives, and of course this convergence is uniform on compactor, because if z naught varies within a compactor, within a compactum, then we can basically choose the same contour, the same loop. Well, but that was a standard proof. Anyway, let me now discuss the automorphisms of all the model simply connected Riemann surfaces. And this is, of course, also known from the standard course. But it's important to discuss because it will play a special role in complex dynamics. So the first thing is that the automorphism group of CP1, so here by automorphisms I always mean conformal automorphisms, or which is the same thing, Riemann surface automorphisms, all biholomorphic maps from CP1 to CP1. And what are these maps? So these are all the fractional linear maps. Да. Есть довольно общая теорема из комплексной алгебраической геометрии, которая говорит, что если у вас есть алгебраическое проективное в CPN, если у вас есть алгебраическое многообразие в CPN, ну, точнее так, даже начать с того, что если у вас есть аналитическое многообразие в CPN, оно обязательно алгебраическое, и, соответственно, все аналитические отображения, глобальные аналитические отображения этого многообразия в себя там, или в какое-то другое многообразие, они тоже будут алгебраическими. Вот. Но это такая довольно сложная теорема. So there is a theorem to the effect that in the category of analytic submanifolds of CPN and the analytic maps, you can always say that these manifolds are algebraic manifolds and the maps are algebraic. So analytic and algebraic means the same thing if you live in CPN and if you consider global objects, globally defined manifolds and globally defined maps. AZ plus B divided by CZ plus D. So this is exactly the group of all A, B, C, D are complex numbers. And the determinant is not equal to 0. AD minus BC is not equal to 0. So this is the same group as the projective linear group of 2 by 2 matrices, non-degenerate 2 by 2 matrices, modular non-degenerate scalar matrices. So if you multiply by the same number, if you multiply all coefficients by the same number, then nothing changes. It's the same fractional linear map. So why it is so, let us not discuss why it is so. This is standard, okay? Or shall we? No. Okay. We will not. Now, the second claim is that the automorphism of C is what? The automorphism group of C. So yes, this is the group of all affine maps, affine transformations, A, Z plus B, where A and B are complex numbers and A is not equal to 0. So this is a complex group of dimension 3 because you have 4 coefficients but 1 excessive degree of freedom because you can multiply all coefficients by the same number. So 4 minus 1 gives 3. Now this is also a complex group of dimension 2, right? And it's very easy to deduce from this because any automorphism of C extends to an automorphism of CP1 by the removable singularity theorem. You just have a removable singularity at infinity, okay, or change coordinates and make it a removable singularity. Then you observe that if infinity is mapped to infinity, then C must be equal to 0. Otherwise, infinity will be mapped to something else. Okay? So C must be equal to 0, and since C is equal to 0, then we get affine maps. Now the third automorphism group is that of the disk. And for the disk, the automorphism group consists of all maps of the form e to the I theta z minus a divided by 1 minus a bar z, where theta is a real number, or if you wish, real numbers modulo 2 pi z. A is some point in the unit disk. So in contrast to the two previous cases, in this case, this is not a complex group, which should be no surprise because we have some restrictions of not complex. The boundary of D gives you some real type restrictions. And it depends on 3 real parameters, so this is a real group of dimension 3. A gives you 2 real parameters, and theta is another real parameter. And why this is what it should be, if you have an automorphism of the disk, so if F is an automorphism of the disk, then you must have some point that's mapped to 0. So you can say that there exists some A such that F of A is mapped to 0. And this will appear in the numerator. So in general, maybe this is not this was not the right place to start. The first place to start is that if you have a conformal automorphism of the disk, then it can be extended as a conformal automorphism of the entire sphere. Why? No, we want to prove this formula. We do not assume this formula. We want to prove it. So if you are given a conformal automorphism of the disk, then you can use the symmetry principle. Do you know the symmetry principle? So you can reflect in the disk and extend the map by symmetry, so that symmetric, so all points split into pairs of symmetric points. Actually, we don't have to know that. There are 2 different versions of the symmetry principle. It's automatically, if you know that the image of the disk is the disk, then the map automatically extends to the boundary. It's another theorem of complex analysis. Anyway, so how to extend it to the outside is to say that all points of the plane, apart from those on the circle, split into pairs of symmetric points. You can reflect in the circle. So if you have any point Z, say inside the circle, then there is a symmetric point Z star outside the circle, where the symmetry is the usual inversion, the usual geometric inversion in the circle. So you may know what an inversion is from high school geometry, but it can also be defined in conformal terms because you have a family of circles through the 2 points, through Z and Z star. You have a 1-parameter family of circles, and if the 2 points are symmetric to each other, then all the circles are perpendicular to the unit circle. So all these angles are the right angles. Then you say that you can arrange a map defined on the entire sphere, which sends symmetric points to symmetric points. And in this way, given only the map in the disk, you can define it extended outside by symmetry. And the symmetry principle tells you that this map will be holomorphic. Therefore, it will be of this form. Now, we already know what happens to be in the numerator, Z minus A, because A is the point that's mapped to 0. Well, up to this constant, of course. But then the numerator is determined by a point which is mapped to infinity and which is necessarily located outside of the disk, right? And it will be symmetric to A just because we extended the map by symmetry, right? It will be symmetric to A, and this gives you the denominator. The symmetric point is 1 over A bar, okay? So if Z is here, then Z star is just 1 over Z bar. And the coefficient just must have modulus 1, which is also clear. Okay, so we discussed all the automorphisms group, all the automorphism groups. Well, what happens next is that Milnor discusses commuting maps, and in terms of their fixed points. So let me maybe repeat a part of this discussion, not all of it. Ну, нет, ну с точки зрения пропорциональности это то же самое, да? Вы спрашиваете теперь про коэффициент при всей дроби. Правильно, да? Коэффициент при всей дроби. Но коэффициент при всей дроби можно понять вот что если z лежит на единичной окружности, то эта дробь по модулю равна единице. Но это такое простое вычисление. So what we need to say about this overall coefficient is that its modulus is equal to 1. And this is the same as to say that if z is on the unit circle, that is, if the modulus of z is equal to 1, then this ratio has modulus 1. This is a basic computation. Is it okay? Shall we do this computation? No? Fine? Okay. Да. Да. Ну, хорошо. Да, ну хорошо, что мы хоть что-то сделали не как обычно, да? Не получилось не как обычно сделать. А у Milnor написано, что-то вот как-то там это самое все. Вроде все просто, но не запоминается. Ну ладно. Как там ловко очень делается, по-моему. Ну, читайте. Okay, so what we need to discuss is the relationship between commuting automorphisms and fixed points. So let me first say what I mean by commuting automorphisms. Commuting means commuting with respect to the composition. So f and well, let's say that f and g in an automorphism of something are commuting if f composed with g is the same as g composed with f. And the basic lemma is that is that we can say something about the fixed point sets of this automorphism, assuming that the two automorphisms commute. The fixed point set is just the set fix of f, which is the set of all points z in X, such that f of z is equal to z. The points that are fixed under the action of f. Basically, well, one thing to note is that the commutativity condition like that is already a dynamical type condition, dynamical type of condition. It can be rewritten in the form that f is conjugate to itself by means of g. So if you conjugate f by g, then you get the same map. And this is a dynamical statement. In particular, if you well, in general, the fixed point set of a conjugate map of G inverse F G is what? Let me put it like that. G inverse F G. Can you say what it is in terms of the map itself? In terms of the fixed point of the map F? Mm-hmm. Yeah, you simply apply G to the fixed point set of F, right? Because this is the commutative diagram. So here you have F, here you have the conjugate map, G, F, G inverse, and here you have G, right? And everything that happens above is mapped by G to the corresponding object below. So if any, moreover, this is G respects the dynamics. So whatever number of times you iterate F, so if you have an orbit of a point under the map F, then downstairs the image under G will be the orbit of the corresponding point under the conjugate map. So in particular, if you have any periodic cycle, then the image of G will also be a periodic cycle. So the same applies to the fixed point set. If you have a fixed point, then the image under G is also a fixed point of this map downstairs, and the other way around. So that this is always true without any assumptions of commutativity. And the second thing, if they commute, if F composed with G is the same as G composed with F, then the fixed point set of F is invariant under G. Well, which is immediate from the first part. Well, using this basic lemma, we can say something about commuting automorphisms of each of the simply connected Riemann surfaces in terms of their fixed point sets. For example, if we, let me call it a proposition, if we take C and look for commuting affine maps, then we can say F and G commute if and only if they have the same fixed point set. If they are not identity, right? Minus the identity. Identity commutes with everything. That's true. And otherwise, if an affine map is not the identity, it has a single fixed point, which must also be, so if F has a single fixed point, then this point must also be fixed by G. So they will have the same fixed point sets. Or F has no fixed points. Then G also has no fixed points, because any fixed point of G must be invariant under the translation performed by F. And that's a contradiction. So this is maximum one-point set, and this is equivalent to commuting. okay, for let's consider the Riemann sphere. So this is another proposition. X is the Riemann sphere. In this case, and again, we consider F and G, which are automorphisms of the Riemann sphere, but not the identity. Then any automorphism has either one or two fixed points. Can you give an example of an automorphism with only one fixed point? Yes, Z goes to Z plus 1 is a so-called parabolic map. So in this parabolic case, the fixed point at infinity, is degenerate. That means that the two fixed points merge together. Now, if you have Z goes to lambda Z, then this map has two fixed points, namely 0 and infinity. And these are basically all the cases. Now, if F and G commute, then either they have the same fixed point set, Что? Еще раз? Две неподвижные точки. Ноль и бесконечность. Да, да, совершенно верно. Well, and in general, so you may also want to study the dynamics of this map, but it's somehow trivial. Still, it may be important to understand the dynamics in this case. So if the modulus of lambda is not 1, then among the two fixed points, one is repelling and one is attracting, in the sense that all orbits different from the two fixed points converge exponentially fast to the attracting fixed point and are repelled, again, go away exponentially fast from the repelling one. Well, if the modulus of lambda is 1, this is just a rotation, and this is also clear. For this example, all points converge to infinity. But sometimes in a non-trivial fashion, because even points that are very close to infinity may converge to infinity in a strange way. So imagine a point with a real part whose real part is a large negative number. Then this point is initially close to infinity, but instead of going to infinity right away, it goes to infinity, but through all finite places. Почему они коммутируют? Ну, well, the question is, suppose that we have this, then why they commute? Because, well, this, I would say this is again a basic computation, because we can always put this fixed point to 0, and then both F and G will be just multiplications by different factors. Well, I don't know, but this computation is so basic, then it's almost like no. Okay, if F and G commute, then either they have the same fixed point set, or they are both involutions that, so then, or Another case is that f squared is equal to g squared is equal to the identity. And f permute the fixed point sets of each other. So, of course, the fixed point set of f is invariant under G, but it does not have to be pointwise fixed. G may interchange the 2 points, and this happens. So it happens that f interchanges the 2 fixed points of Z, or f interchanges the two fixed points of G, and G interchanges the 2 fixed points of f. Okay? F interchanges the fixed points of G and the other way around, and vice versa. Okay, this is the statement. And the example of the second case is what? Say f of Z is equal to minus Z, and G of Z is equal to 1 over Z. So here the fixed points are 0 and infinity, right? And here the fixed points are plus or minus 1. So minus Z interchanges the fixed points of G, and 1 over Z interchanges the fixed points of f. So this is how this case works. Okay. We don't have time to prove this, but maybe, well, I don't know. This is basic. This is very basic, and it's written in Milnor. I'm not sure. If you wish, we can discuss it next time. If not, we will just go on. Mm-hmm. Any other questions? Okay, thank you. До свидания.